Very good. Okay.
All set.
All right. Thank you. Good morning, everyone. Thanks for joining us. Today, we're going to cover the introduction to alternators and generators. It looks like we've got various levels of experience in the experience field. Thank you for putting that in. Quickly, my background, I did power generation work. I did engineering work. And from an engineering design standpoint through chief technical officer to CEO for different businesses throughout my 40 years, and retired now and enjoy teaching for EXA. So in the years of teaching, I've learned I don't read the slides to you. So feel free to read the slides. I'll have them up there for a minute. If you have any questions, pop them up at any time, please. I'll try to watch the chat box. If not, just jump right in and say hi. But this is where we're headed. Feel free to read the slides as I go along. And there'll be parts that go pretty fast, and there'll be parts that go a little slower. So again, give me some feedback if I'm going too fast or too slow. As you know, the primary sources of electricity we have on the market today are stored energy, and often in the form of batteries. It could also be other storage. We have solar and wind, and then the industry we have and love is this rice industry, reciprocating internal combustion engines, that what's also known as spinning iron. And so the vernacular of today is, I've got to turn that dinging off somehow. Okay. The generating system is typically spinning iron or IFG, inverter fed generation. And why this matters is the type of inverter we get into. Most of the static systems today convert DC. Even your wind turbines will convert AC generated to DC back to AC again, because the initial generated AC is varying in frequency. So they convert it back in again. So, and when it comes to controlling inverter fed generation, that's where it gets to be tricky. That's where we have to draw the line. So with spinning iron, we typically have the two types here: alternating current, direct current. Alternators typically, or by definition, alternators produce the AC, generators produce either AC or DC. I've used the term interchangeably. A lot of people have. Technically, most of the ones we deal with today are alternators, but we use the term generator quite a bit as well. I personally, I don't think it matters in our discussion of which one we have, but I'll probably use them interchangeably today, as I have of my career. So, well, we're not. There we go. Okay. And as you know, the spinning reserve we deal with is, and it's a term we need to understand, is all the KW being produced in the online sources today minus what's being consumed at any point in time is this spinning reserve number. When I started in the industry in the early 80s, the spinning reserve on the grid was about 22%, something like that. Today, it's like 2%. So the spinning reserve has dropped dramatically over the years. It saves energy, sure, it saves fuel consumption, but it also makes for a more delicate grid. Impacts come along that can cause problems, and you have to respond to that, which is evolving the smart grid as we know it today. Also, there's an operating reserve, which is ready but not online. So these would be cold generators, if you will. Most of our standby gen sets fall into this operating reserve category. And typically, spinning reserve runs about half of operating reserve. So there's still generation out there available to go at various times, starting times from a few seconds to a few hours, depending upon the type of generator. And why is this important? This is because there's so much so much interruptible power, inverter fed generation being put on the grid today that we're actually starting to see regulatory agencies like California's ISO and Texas ERCOT are coming back saying, if you're going to put power on the grid, you need to have spinning reserve available to offset any power you put on the grid. So we're seeing changes in the grid today, and it's important. Here's some data from EIA. The total energy produced over the years, this is always back from 1950 to 2020, a quick peek of that. You can read that on your own. You can pull it up on EIA.gov. But coal passed wind here, and although this is the history going back 50 years of data we've got, I think some of the important part of it is the last few years, since the last 10, let's say, or 11 years from 2012, you see coal past wind, excuse me. Here's wind down here at the bottom. It's steadily increasing. Hydro's pretty flat. Nuclear's pretty flat over the years. Hydro is down some with the drought. You see it here. And solar's coming up. And here's petroleum-based power generation down here at the bottom. So this rice industry is the fastest responding, but it's also the smallest when it comes to total mega kilowatt hours of power produced and consumed in the U.S. This is power consumed, not immediate kW, but energy in kW hours. So some numbers behind it all. And you can read this, like I said, as you need to, as you like to. But the point is that solar and wind together make about 18%. We hear a lot about it, but it's still only about equal to nuclear. Still by far the largest is natural gas. And we have others that come into play, but typically most of the solar and wind are grid following inverters. And anyone out there understand the difference between grid following and grid forming inverters? Anybody deal with this part of the industry? Okay. The grid following inverters are what's on most residential homes, and they can only produce power if the grid is there. They supplement what is there on the grid. Where a grid forming inverter, it would be able to actually be a frequency regulated and voltage regulated source, stands alone on its own. So that's a more expensive system and not used as often as the grid following inverters do. So here's some solar data. Again, we're looking at where power comes from. Solar, SEI data is about 1.5 billion watt hours of installed capacity. Inverters about 95% efficient. So there's some issues that come up with solar. Why aren't we getting what we say we're going to get, right? We have a capacity utilization of about 22%, so only a fraction of the power that we expected to get from solar getting. And so I know some of you deal with remote power sources and are using solar. If you can help some of this, but things I've seen so far that are leading to solar is the panel efficiency, the orientation, the weather maintenance, all these things feed into this solar power segment of the power we provide. But it's actually been curtailed quite a bit by ISO because of an oversupply is driving the grid unstable. And that's called the California demand duct. We'll look at that in just a minute. So it's being curtailed, and also the end of the subsidies has caused some issues and some financial problems. Net metering went away, market confusion, if you will. So solar's here. It's probably here to stay in some areas. It's not a huge part of our power generation today, but it needs to be done carefully and take more controls in order to bring it on safely and make it and keep the reliability of the grid. And that's because most of the solar we see today are grid following inverters and not grid forming inverters. And so they cannot stand alone on their own. That's changed in the last few years. In California, they started allowing a grid forming inverter to be the primary backup source for a hospital, which was not allowed in the past under some regulations. So we're seeing changes in the system, but still there's growing pains, if you will, with solar. Wind power. Okay, we've got the wind power system. This is from as a map we can pull up if you'd like to see it sometime from there, if you want to type that address in, look at it. But there's about 142 gigawatts of wind turbines and about 72,000 of them. They provided 10% of the total kilowatt hours, or 435 billion kilowatt hours total energy provided to the grid. And they're about 35% capacity utilization. So capacity utilization would be like a 1 meg generator running all year long, 24/7. There's 8,000 hours in here, so that would be a capacity utilization if it produced 8,000 and whatever megawatt hours. So most of the wind power, again, are single mode inverters, which still rely upon spinning iron to be the backbone of the grid. So what does this sum to? Well, industry trends we're seeing is that we're shutting down some of the coal system out there, and there's units are being retired. Things are pulling forward from there. the SCOTUS reversed the Mercury Air Standards Act. Illinois passed a law that all coal offline by 2045. We're shutting down nuclear plants. Some of the big gens are coming offline. We did bring one. Google Vogtle number 3 came on this year, about 6 years and 100% over budget. So nuclear is there. It's been a solid backbone, a high capacity utilization, but they're really not, it's not enough to do what we need to do. And we're having trouble with grid recovery. And those of you that deal with small markets who understand this real well, is that if you have a lot of inverter fed generation, especially single mode inverters, bringing it back on after an outage is a problem. We saw that a few years ago with Texas in the winter. We saw it in California in the summertime, saying, hey, our grid is becoming unstable because we have so much of this inverter fed generation. It's wind in Texas, it's sun in California, but they have so much inverter fed generation penetration ratios that the grid is becoming unstable. And we have to do things to prevent that. So we're having some growing pains, and that's what grows into what I call the first 15. And this is an engineering thing you have to work into your theories, and when you're designing a power system, is that the first 15 minutes after a disturbance, you protect, minimize. So this example would be a car hits a power pole. So in the first 15 milliseconds after that, you want to minimize the outage, detect and protect and minimize. The next few milliseconds, you want to switch your short-term energy storage into discharge mode. You alert alternate sources, so you send a signal out to your RICE unit, say, hey, get ready to start, right? That's the first, comes out right off the bat. The energy storage would be like the compressed air energy storage, the battery energy storage, the air energy storage are switched to discharge mode to support the grid, to keep the rest of the grid up. In about a second and a half, you shed your non-critical loads, send an interruptible rate contract load, says, hey, I'm going to take you offline. I'm in what's called a time of constraint. I don't have enough power on my grid. My spinning reserve has fallen too low. I need to do something to support my critical loads on the grid, and so I'm going to isolate. Also, at this point, you can shut down all your HVAC systems, your hot water heaters. If you turn the air off in your office for 15 seconds, you wouldn't even know it. You shut off the hot water heaters. You shut off any, induction furnaces of any kind, refrigeration. Take all that load off quick in the first second and a half, and then at 15 seconds, you can start your RICE engines. You can also replace loads by kicking in the interruptible rate contracts and pushing loads over to the generators. And at this point, you might be able to allow some less critical loads back on. At 15 minutes, you'll start your combustion turbines for grid support and allow the rest of non-critical loads back on. And an hour and a half, you do your fast start steam turbines that are out there that are available. It takes about an hour and a half to start a steam turbine from dead cold. And then if it still goes on longer, you can then add your base load, or what's nicknamed dirty steam turbines, those that come up quick, and then the coal scrubbers or output scrubbers are added later on. So this is the essence of the microgrid, is this ability to communicate this information back and forth, and you can stop at any point, go back the other way, bring your power back on. But this is what the grid of the future will be as we try to implement more and more inverter fed generation in there. And then energy storage is also critical. Questions? No? Okay. And again, energy storage is going to be a critical part of the future out there. There's a lot of different energy storages out there, whether the energy be thermal energy or whether it be watts chemical energy in the form of batteries. It might be kinetic energy in the form of spinning flywheels, but the supercapacitors, there's different types of energy out there, and we're going to be storing energy. This is a big field we're all dealing with today. Batteries certainly are there. As far as how much they can control, yeah, that's to be seen, right, as we go forward. They have big conventional or flow batteries that flow two chemicals past a membrane to produce power. That's a huge amount of kilowatt hours, plus your kilowatts, your peak capacity might be limited by the size of the inverter. There's lots of factors that come into play energy storage as we go forward. It's a very key market we have to deal with. And so what's the difference between a parallel and a smart grid? Well, the RICE gens one or more loads. You use you add this in the RICE into the system. 3 or 4 generators in parallel with them become what's called a parallel power island. This might happen more often than you might think. You've got your inverter fed generation. So it's if you add IFG to RICE, you get a microgrid. And that it's really pretty simple as long as you stay with a low penetration ratio. So if you keep with, a third of your power from your load profile, a third of the power comes from solar, you just let it looks like negative load to your generator. It's just not there. It's being supported by solar. But as it starts to get more and higher penetration to the point you can start pushing the generator around, or you can get generator into minimum power, or you start having frequency of voltage issues, then you need to take more control steps to do that. And that's when it becomes more critical and you have to do more controls. But small amounts of power on the grid, like it has been in the past, it's not a lot of control necessary. Only when you get into bigger percentage, then it becomes a problem. And we've seen the bigger percentages in Texas and in California with 2 recent incidents. So the other one is the IFG primary. And again, this is where you have a large battery, a large inverter that can supply the entire load. And they allowed this at a hospital in California just recently, like I said, and obviously about 5 years ago now, 6 years ago. And the gen set is just regulated to be a battery charger, essentially. Your batteries get low, run the gen at its most efficient point, charge your batteries up, shut it back down again. So we're seeing changes in the system as we accomplish these new goals with electronics and controls. So, and I know this is not alternators necessarily, but there's some interest in this information. So I added it for you guys' schools, this information up front here about where our power comes from and how we control it. And I say that the inverter fed generation is like towing a charger behind your Tesla. So if you drive down the road, you start the generator and keep you going. And that's kind of what we're seeing with systems today where inverter fed generations become primary. The problem you run into is with impact loads. And that's that hospitals on the MRI, because there's that thump, 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 thump of the MRI magnet all the time. That plays havoc on generator control systems. And that kind of load is often better fed from a reciprocating engine, a RICE genset, than it is from inverter fed generation. The IFG systems, the inverters just don't have the VARs to support that. And of course, the difference is the control system, right? Whether you're going to get into the point where you have below 30% penetration, it's very easy. All you really have to do is protect the generator against reverse power, and all you have to do is turn the inverter off. So you send a contact at some low power level, shut off the generator, or shut off the IFG. When you get into higher penetration in the grid forming inverter, then your control system needs to be much more. And it's companies that do just that, make control systems up for these microgrid applications. It's a new business that's found its footing in the last few years. One more interesting topic that I'd like to talk about, and that is, we've all heard about how bad coal is, or how bad diesel is, and how dirty diesel is. Well, I'm sure Michael talked about advances in engine technology have come along in the last few years, especially to the point now that if you're only dealing with CO2, we can actually show that burning diesel is less CO2 than coal. Here's a power plant from Illinois, Coffee in Illinois. It's since been shut down, but it's a 1960s era coal plant. In 2014, it burned 2.7 million tons of coal and 637,000 gallons of diesel to make 5.2 billion megawatt hours of energy. So if you run that into BTUs and do the conversion, you'll find that overall is about 32% efficient, which is about what you expect on a plant. And in that process, they produced 247 of per megawatt hour of CO2. Well, with a T&D losses, which you get with a distribution system, that means a net efficiency around 25%, where if you put distributed generation around the countryside to feed it at various places and didn't have the T&D losses, and you're running a tier 4 engine, you actually end up with about 1,500 pounds per megawatt hour of CO2. So today's diesels are much cleaner than they used to be. As my friend Michael likes to say, this ain't your daddy's diesel. And they've changed a lot since then, and they've made vast advances in them. So they're not as clean as gas in some areas. They do put out other things that natural gas does, but we've seen a big difference in diesel in certainly the last 10 years with the efficiency of diesel engines. So we're going to jump into generators now, a little more of the generator theory. That was a pretty fast blow, I know, through where our energy comes from today. I'll pause for 1 second to get a drink of water and let anybody pop up any questions, either verbally or in the chat box. Okay, well, let's move on and get into the generator side of the equation now, which is what the title of this class actually is, but that they ask for a little more background on where power comes from and trends in the industry, because certainly as I understand it, the military has been very supportive of making your bases independent, their own little microgrids. And those are some things to think about in your microgrid design and implementation. So a little fun with physics here. We've got as you remember from your beginning classes, there's a relationship between current and magnetic field. It's called the right-hand rule. Current flows and magnetic fields formed around the wire. And also, I must ask one question here. Have those that know the difference, have you been trained in electron flow or in conventional current flow? If you've been trained in electron flow, drop a note in the chat box. If you've been trained in conventional current flow, it'll be the rest of us. And I'll go on and explain the difference. Electron flow, technically electrons flow out the negative terminal and into the positive terminal. And many places for a long time taught that electron flow that direction. One of the places that taught it was the military. And I don't know which branch or which area, but I have had students in the class in the past that were taught electron flow. Throughout the classes today, we all use conventional current flow. So my right-hand thumb analogy, my right-hand cross product we're going to use for the definition of an alternator physics will be based on conventional current flow. So you don't know the difference, you're trained in conventional, don't worry about it. If you were trained in electron flow, please work with us on the conventional current flow model, because it's much more commonly used today. So current flow in conductor, magnetic field around it with the right-hand rule. As we opposites attract, as we know, we put north to south, and they push each other apart. Three-way relationship, which is the cross product, as it's called in physics, between current, field, and force. And there's a right-hand rule for generators. So if you move a conductor through a magnetic field, you'll produce a current flow. So your motion is with your thumb, the field flow, the B lines, magnetic flux lines, or your index finger, and of course the middle finger then becomes the current flow. And the opposite is a left-hand rule for motors, with the same basic, field motion and current principle, but on motors it's the left-hand rule instead of the right-hand rule. So conventional current flow in the wire we see here, get my laser pointer up here on my screen. Here we go. So we've got our sorry, technical difficulty. If you put that coil of wire around, you'll see that it becomes a stronger magnetic field. And as you move that magnet past the coil of wire, it actually produces a voltage. And that's an important concept, is we produce a voltage. We don't produce a current, technically we produce a voltage. What happens to that current is the load the customer applies. And you've probably seen something like this in the past, or maybe did it where you actually ran current through a wire, and these magnetic filings, magnetic particles, then come into lines. And so we drew the magnetic field as a group of lines showing the strength of the magnetic field. It's just one way to visualize what's happening with the magnetic field. So that's the physics behind it, is the relationship between current and magnetic field. And now let's look a little bit of how they're made. So we'll start with the rotor, and then we'll later on we'll look at the stator. So we'll start with the rotor first, which is the one on the right, and later on we'll talk about the stator assembly. So again, back when I had gray hair, back before I had gray hair, we used to literally dig a hole in the ground, pack it full of sand. Special molds were put in, steel was poured into it, made a casting, and a very large casting in the ground. It was let to sit for a while till it cooled. You pull the casting out of the ground, you find the center of it, and you start grinding away. And you grind away and mill it away, and after a while, you take this rotor, ends up looking like that. It takes a while, but eventually you end up with a machined rotor. And I use pictures of larger machines just because it's easier to see. The same principle applies right down to the small machines, but I have a few pictures of small machines, but mostly they're large machines just because it's easier to see. So here's your journal bearing on here. There's a hole down through the shaft where cables come down through the middle of the shaft, and this machine is milled and turned and machined to be a finished product like this, ready for winding. Here's one on the stand, just getting started. They've put this in. If you can look at this real carefully, if you have any guesses what that might be, popping out of the middle of the shaft there, actually is, you see it here again, it's a field current bushing, zoomed up a little bit. So field current's coming down the shaft and coming out that bushing. So this is the kind of orange part is insulation, and here's the conductor at this end. I'm sorry, it's not the great picture, but it's been zoomed way up. But in the next one, you'll see it here. It's connected to the frame. So this is the field current to feed these copper windings that are laid on the shaft here of a cylindrical rotor machine. You have large conductors to carry a significant amount of current. As you probably remember, the strength of the magnetic field is equal to amps times turns. So you put lots of amps, in a few turns, you produce a very, very strong magnetic field. And with that consideration, if I have 2,000 turns at 50 amps or 10,000 amps at 10 turns, which one is a stronger magnetic field? Anybody? What makes a stronger magnetic field?
Let's say the current flow.
Yeah, they're the same. Kind of a tricky question. It's the same, right? Because 50 times 50 times 2,000 and 10,000 times 10 is the same thing, right? So thank you for joining in, but it's a bit of a tricky question. It's the same. Why would you do that? Why would you bother? Because large amounts of current are difficult to control versus a smaller amount of current, right? Smaller current, higher voltage, lower current, lower voltage. But why do we use more? Well, there's less total inductance in the system, and our generator is better able to respond to increases in VAR flow. Typically what you see in a disturbance. And disturbance can either be a fault, literally a fault on the lines, phase to phase, phase to ground fault, or it can be a large inductive load like a large motor or a large transformer. Anyway, those all take VAR flow. And so we can respond better and faster without the inductance in the picture. Now, we've done things on the regulator side and we can show you that. We look at the response curves. We've added forcing. We've added, a differential PID, and the differential regulator used to just be PI. Now they're PID. So we've added things along to compensate for this time constant. But still, the time constant is a factor in how our machine responds to a large bar flow, and so it gets a better time response. So here's one that they're doing some inspections. You see these copper windings laid in here. They're insulated from winding to winding. And he's looking back in here trying to do some inspection. Once they're laid in place, they're blocked and held and wedged. You see a wedge up here on top. My annotation on here. Well, I'm sorry. I was trying to make my annotation work, and it's not working for some reason. But there's wedges laid up here to hold these in place. So there's turn-to-turn insulation, and this is going to be the field current to ground insulation. It's not phase. This is the DC side, but there's insulation to ground as well as insulation between the windings, and they're wedged in place and held in place and tested. A lot of labor laid those in there and test them that way. Here's some pictures of stampings. Now, we talked about that was a cylindrical rotor machine machined out of a casting. Now you can take a salient pole machine, and a salient pole machine are laminations that are stacked. And so you're stamping these laminations, stacking them together to make this rotor. And then windings will be wound around these rotors when we get there. This is a 4-pole machine, obviously. The previous one was 2-pole. Look down the bottom part of the picture to the left, you'll actually see the stator laminations that are stamped and ready to be stacked. So these are, I believe, wind turbine rotors that are being produced here out of stacks of laminations. We end up with a salient pole rotor, and this one is out of a solid iron here, and just rhetorically, why is that so thick? If you look at this, you've got individual poles that are wound, and it's being held on by a strap right now because they took a couple off the bottom down here. They've taken one off here to be rewound. So something happened to these, probably turned shorts internally, and they were taken off and they're being rewound and put back on again and repaired. So it's a little easier to fix these when it's a salient pole rotor, to unbolt these and pull them off. You can see the wires coming here that bring smaller amount of current, higher voltage a little bit, maybe 60 volts, maybe 50 volts, something like that, but a small amount of current here, relatively speaking, compared to the other one. And here's your slip rings here that bring the current onto the shaft from brushes. Okay, so why is this iron so thick? Well, it's got to conduct the magnetic field from north, south, north, south. These poles vary all the way up and down around here as these magnetic field is then rotated or spun past the conductors in the stationary part to make the voltage. So I always figured if I knew how something was made, it's easier to fix. And I repaired and fixed these machines in my career. Any questions? I'm still looking. I don't see any questions in the group chat. So any comments or questions, feel free to speak up or put them in the chat. Here's one more picture of a rotor, give you a concept of size. And I bring this up because the backbone of our grid, it needs to be a solid, frequency source. And so this is a huge amount of inertia. This is a dam in China, Three Gorges Dam. This particular unit is 785 megawatts, about 45 feet in diameter, 13.1 feet high. So the pole face here is 13.1 feet. It's all in metric, so I converted it over. So pardon for the strange numbers, but it's 1,488 tons, 80 poles. So if it turned 50 hertz, that'd be 75 RPM. This is a huge amount of inertia spinning, fed by water through a hydro plant. I know you can't see it in here. It's just a fun sidebar. There's a guy down here in the bottom somewhere that's directing this. He's standing there underneath this 1,488 ton rotor with his arms stretched out one side. They're saying, go this way, go that way. But he's got his hard hat on. He's ready. So anyway, this kind of inertia is what we have in our grid today. If you parallel even your 2 meg machine up against this guy, and it had some kind of fault in your machine, it wouldn't even see it. It just blow your breaker on your machine, and they wouldn't care. So generally, the utility doesn't care about your generator at all. They care about what happens to their grid. They don't want you backfeeding their grid and hurting their people, but they don't care about your generator. So you're insignificant to them. So quick review of rotors. You can either make them a cylindrical or a salient pole rotor. A cylindrical rotor typically is machined out of a casting, or it could be stacked laminations, but typically machined out of a casting. High current mini windings versus low current. High few windings, low mini windings. Again, it's this time constant of the response of the field to a disturbance in the system. Typically, because of the way they're made, these machines tend to, if you're going to have a high-speed machine with all that weight, you can imagine a huge amount of weight on the rotor, all that weight on the rotor, that it actually is a high-speed machine. Works better in that application to be that type versus a salient pole with you spend those big heavy windings at 3,600 RPM. That's a huge amount of inertia and centripetal force out there. So, and you look at the weight deficiency, the bearing, things like that have gone into manufacturing in the last 20 years, have been able to make us bring these rotors down in size. We get the gap down, the bearings are better, the insulation is better. And so machines over the years have gotten better and better and smaller and lighter because of better manufacturing. And the salient pole machine, again, those are stacked, typically stacked. They could be machined, typically are stacked. Generally uses a lower amount of current, many windings, and typically a low speed like we saw in that one from Three Gorges Dam. Very, very high power applications. In either one of them, we've got to get DC on the shaft. And so there's a couple ways to get that DC on the shaft to produce that rotating magnetic field that's going to spin past our stator when we get there. So this pulls us into the exciters. Now, how do we get the current on there? Well, 2 ways. One is through slip rings and brushes. And there's pros and cons of these. The response time tends to be the biggest biggest advantage, if you will, versus a PMG setup. But they do wear out over time. These are graphite brushes on a bronze slip ring, and they do wear over time. And they're susceptible to difficult environments like high humidity, salt, sand, things like that tend to wear these brushes down even faster. And, of course, it never fails when it's convenient. You're interchanging these brushes when it's the worst conditions. So they do wear out versus a rotating exciter has got no touching parts, moving parts, yes, but no touching parts like you do in the slip rings of a machine that's fed from external source. The PMG source is a rotating exciter. And so there's extra hardware on the shaft. There's extra components that make this up. The shaft's more expensive, but it's got no parts to touch, and so it doesn't wear out. And so you'll see the other windings on here. Here's rectifiers on here. Here's some filtering back here on the shaft. Here's bringing the cables to this external salient pole machine. You can see all the windings and rotors. This is a big, slow machine of some kind. We're seeing these well-made machines go 60, 70 years. Nuclear power plant operators today, they first got licensed to go 20 years. Then they got up to 40 years. And now some are going back for a third registration with the NRC to go 60 years on the same generator. It's pretty amazing that makes it last that long, that level. So the brush and slip rings, you can see them here pretty well. There's copper pigtails that bring the current from the brush rigging, which is connected to these wires, and that brings the current onto the shaft. And you can, then here's the other pole. So you got plus and minus. Obviously, it looks like the red wires here. So this is the plus and this is the minus. Then current's delivered onto the shaft. Then it goes down the shaft to the center of the shaft to the windings. You can see the windings over here. Rotating exciters, on the other hand, again, most of our industry is using PMGs. I'd guess over 90% are using PMGs. So I talk a little bit more about these and how they work. They're very common, self-contained, very low maintenance. They do, however, have diodes on them that must be checked at every maintenance interval. And the analogy I draw is that if you have one cylinder out in your vehicle, say if it's an injector on a diesel or a spark plug on a gas, if you're missing one cylinder, will you still make speed? Think about that for a minute. Can you still make speed if you're missing one cylinder on your internal combustion engine? Anybody?
Depending on the number of cylinder?
Could be. Would you think you'll still make power? You make full power without that cylinder.
Probably not full power, but it will be at a certain percentage.
Right. You'll lose. You can still make speed. You can still make power, or actually you can make torque, I should say, at a lower speed, but I doubt you'll make full power at full speed by missing a cylinder. Similarly, in a rotating exciter assembly, when you have the diodes involved, you'll make full voltage. You might even make full current at a lower voltage, but you won't make full current at full voltage when you're missing a diode. So it might also takes a little more response time with the PMGs. For a bus fed or a compound system or separately fed systems, those are higher controlled. They can feed off of themselves. I can't draw it on the screen there very well, but the output power is then brought back in to do the excitation and bring it online. So a little more maintenance to it. There's some short circuit considerations. If you have a high load or a short circuit on a compound or self-fed machine, the voltage can collapse. And so if your voltage collapses, you don't have enough current to trip your breakers. So you do this slow burning, arcing, welding type of fault, and that's the worst scenario you can have in a power system, as you know. So the PMG, here's the components of a PMG. You can see them on the shaft. Here's the exciter. Here, rotating exciter. To the right are the diode assemblies. And then they go back down the shaft and come out. I don't think you can see them on here, but they come out and run the poles wound on the rotor. So functionally, diagrammatically looks like this. You have a PMG somewhere. Typically, this PMG is 240 volts at maybe 6 or 7 amps. It's not huge, but it's a permanent generator. You spin it and it produces power, no control. What you see is what you get as far as voltage. So that's AC. It feeds the AVR. The AVR then converts this AC into DC that feeds the stationary field on the stationary part of the system, and that produces the magnetic field that comes onto the shaft of the machine that feeds the rotating exciter. So you excite the field with this magnetic field produced on the stationary part of the machine that produces a voltage here, which is AC, through the diodes to DC to the main field. Wow, we went AC, DC, AC, DC. 4 conversions to get there. A lot of extra work, but we ended up saving our maintenance costs, which can be very significant. The advances we've seen in electronics in the past 20 years has resulted in these becoming less expensive. Diodes have come a long ways. We used to buy them by the voltage and by the current. Now you buy them, 60, 80 amps is the least you can get. The rotor is more expensive in this case, but it's like a large power amplifier. Spin it and it produces the excitation for you. So it's easier to ride through faults. It's easier to control, and it's easier to maintain. So a lot have gone this way, even though with the extra components involved. So that's a theory behind a typical PMG excitation system. Again, by far the most common. And these symbols down at the bottom talk about page numbers and chapters in the in the good book, we call it the power generation, on-site power generation guide. And now we've got a typical bus fed excitation system. Would be some other AC source, and it could be another generator, it could be utility, it doesn't really matter, just some other AC source feeds an AVR, which produces DC, which feeds the main field. And of course, your brushes are right in here, this last link before the main field. Lots of amps, low voltage. I've seen these exciters be a wall full of cabinets you walk into. They can be quite large in large power generation equipment. You might need a flash circuit in some cases to get them started. Lots of amps. And again, why would you do this? It comes down to your response time. Okay. Here's some pictures of synchronous machines. I believe this is a steel mill, but here's a large synchronous machine with this exciter on the output. Okay. So here's your rotating exciter running current down the shaft and feeding the large machines. Here's Hoover Dam. Again, same basic principle. I think they have a 2-stage or 3-stage PMG instead of a single stage. So they don't just go right from the PMG to the exciter. They go to an intermediate exciter and the primary exciter. But this starts all with the PMG up here on top. Okay. And it feeds the primary and the secondary exciter, and that feeds the main field. So quite often PMGs are used in our industry. Some cases we use permanent magnet fields for direct supply to machines. Typically, we know the load and we know the voltage drop, and we can design our system with the right amount of permanent magnets to produce this voltage for us. You used to see this in some wind turbines. They would put PMGs on there, and they produce whatever voltage and whatever current they could get. Yes, go ahead. Okay, they produce whatever voltage and current they could get, and put that on the grid. So, and the big disadvantage is you can't be controlled. Okay, we've covered the construction of the rotor of a machine. Are there any questions before we go on to the stator? Okay, we'll keep moving. So now we're talking about the stationary part of the machine and how that's made, and help you understand how to put them together. So typically there's stampings. Stampings of steel that could be fractional. It might be parts of it, but layers of stamped steel designed to conduct the magnetic field. A large magnetic field is going to be placed inside here and spun. It's got to move past the conductors or laid in these slots, and then it's got to come around and get back to the other pole. So there's iron behind these slots to carry the magnetic field over to the other side. These would be partially stacked, stamped. They look like this. They part of the rotor is stamped out just due to the physical size. And then these are laid and stacked in place. These guides keep them lined up with each other as you stack them, and they're held in place on these grooves back here. And then this iron behind stampings carries the magnetic field to the iron frame behind it to bring back to the other side. Okay? So typically these are cut and stamped and stacked on here. And once you've got this steel in place, then you got to put the wirings in there. So the windings this is a random or mush wound wire that's wound on a jig of some kind. They're laid in the slots. And I've got a video I'm going to play now that shows this stator assembly. I won't play the whole thing, and I'll try to talk a little bit on top of it here and there, or show some points as we go along. But here's a short video on how these are laid in.
The stator is lined with slots, each of which holds a copper coil. The more powerful the motor, the bigger the stator and the larger the slots. The first step is to line the slots with insulation. This insulation will keep the voltage confined to the coils.
Face the ground.
The coils are made from several copper wires wound together by programmable machines. The bigger the motor, the more wires per coil.
Each wire is insulated separately. Varnish.
In this motor, each coil consists of 13 strands of copper wire.
Gives a turn-to-turn cylinder that goes out. We'll talk about turn-to-turn in a minute.
Now, workers tie the coils. This prevents the wires from unraveling while being inserted into the stator slots. Workers cap each coil with fiberglass insulation. Then they insulate the portion of the coil left outside the slots with fiberglass sheets. Fiberglass wedges are inserted, locking the coils inside the slots.
Phase-to-phase insulation.
Once all the coils are inserted and insulated, workers begin preparing the connection. They slip an acrylic insulation sleeve over both ends of each coil. 13 coils, 26 ends. Then they group these insulated wires into large power cables. The number of wires per cable varies according to the speed and voltage of the motor. They solder the grouped wires together, then insulate the cables. They tuck some inside the stator and leave others accessible to be attached to a power source when the motor's installed.
Heat shrink sleeve put on there.
Now, using a cord made of heat and chemical-resistant polyester, they bind the coils tightly to ensure they won't move when the motor spins. This unit of bound coils is known as the stator coil.
That process is called stitching or winding. It's important they're tied tightly together to prevent forces when they're pulled apart. We'll talk more about those forces in just a second.
They now submerge the stator in a polyester-based varnish and vacuum it right through. The stator is lined with slot.
Well, something happened. It's called a VPI process where they actually submerge that into a tank of varnish, and they pull a pressure on it, then a vacuum on it, and pressure, and then vacuum again, and it pulls that insulation, that varnish inside everywhere, all the air out of it.
Submerge the stator in a polyester-based varnish and vacuum it right through. This thorough penetration makes the stator coil moisture resistant. The stator is put into an oven for 6 hours at 280 degrees Fahrenheit. The varnish hardens, making the stator coil rigid. Now they have to balance the rotor.
Okay, we'll skip the rest of this part. It talks about the rotor assembly, but so the windings are laid in and stitched real tightly together because the event of a fault, they'll try to pull each other apart. Sorry, I got dogs in the background here. So, okay, let's get on to the next slide. Next slide. There. Next slide. Come on.
The stator is lined with.
Okay, so once they're laid in place, you have phase to phase is this glass cloth. You have phase to ground. There's a plastic cap that's laid on there, and turn to turn is varnish. So these are called the end turns. So the conductors go down the shaft, they come across the end turns and come back the other way. And the number of turns in there and the strength of the magnetic field all play into producing the voltage that we're going to produce. This is a diagram out of the book, and this is kind of a rewind diagram that we get when rewind motors or generators. That shows black, red, blue, the three phases, A, B, C. It's laid in front here, and then it's the end turns bring it down to here, and it's in back. So they're front, back as it goes around, because the distance from these wires to the magnetic field that's spinning past them produces a different voltage in them. So if you kept them to the front all the time, the ones in back would be a lower voltage. So to balance voltage, they go front, back, and they're ABC one after the other laid in here. So this is a 1-to-7 throw into 48 slot core, which means you lay the wires in and there's a center stick which insulates between them. And this is how you generate or create the stator assembly of your generator. This is a smaller, excuse me, this is a smaller mush wound unit. They also do larger form wound. So these are pre-purchased form wound windings that are individually wrapped with, in this case, it was paper, it's all fiberglass, but it wrapped with paper and then varnished. And they're laid into the slots, and these little bars are hammered in between them to hold them in place, and there's phase-to-phase insulation. So you can buy a form wound versus a mush wound machine. The larger ones are form wound. It's the manufacturing process. But electrically, it's the same thing. And when you get these in place, then they're laid in, and you've got some turn-to-turn winding insulation, turn to ground or phase to ground and phase to phase across the coil separator. So A and B or A and C will be, or C and A will be laid in the same slot together. We'll talk about that in just a second. But they're held in place with a wedge. And this wedge looks like it's very large, but the centripetal force is pushing them out. But what they have to withstand is the physical force in the event of a fall. If you remember, the right-hand rule is that when you have a current flow, it can produce a tremendous amount of force to rip the windings out. So any UL 2200 listed machine is type tested. That means they'll make one during the design and manufacturing phase. They'll make a beta unit. They'll actually do a full load short circuit on it. So they'll spin it up to speed, get rated voltage on it, turn the exciter up to maximum boost, and then close the breaker onto a bolted fault. And the only thing that should happen is a breaker trip. There should be no damage to the generator. The generator alternator must survive a direct short and be available to operate after a direct fault. And that's a UL 2200 listed requirement. So they're all tested, and to hold the windings in place, they're stitched very tightly with that polyester cord, and they're also then wedged in place with these wedges to hold them in place and prevent them from moving. So it's forced them to hold it together in the event of a problem. Any questions on that part? Okay. Now let's talk a little bit about the alternator output voltage is dependent upon four things. The first is the strength of the magnetic field. And the strength of the magnetic field as it's exposed to the conductors, of course, is dependent upon the gap as well as the current flow. So a current through a conductor produces a magnetic field. Get that as close as you can to the other conductor to generate this voltage. The speed of the conductors through the magnetic field, how fast you're spinning the machine. The number of conductors. So if you go down that, if you get 1 volt every time you pass that conductor by that magnet, you get 1 volt. If you need 277 volts, you have 277 passes of that wire past that magnet. Now that magnet's will be broken into pieces. It's going to be different poles on the machine, but it's got to pass through 277 times if it's 1 volt. And of course, it's not exactly 1 volt, but that's just an example. So the length of the conductor in the magnetic field, long, skinny machines will produce more voltage per winding than the short, stubby machines will. Of course, there's manufacturing problems with long shafts. There's weight considerations. There's efficiency considerations. A lot of things that go into the equation. But when you're producing the voltage, that's what matters, is the length, the number of conductors, and the speed. So that's how we generate the voltage. Now, the frequency is dependent upon the speed and the number of poles. Okay, so how fast we spin this machine varies our frequency, and how many poles we designed into it. There's a formula that you've seen or will see talking about the number of poles that are there. So which factors determine the generator design? Anybody look at that list up and down? There's several of them that are determined during the design phase of the machine. Obviously, these here, okay, the gap, the number of turns, the length of the magnetic field, the number of poles, those are all defined during the manufacturing process and can't be varied after the fact. So if I want to vary my output voltage, how am I going to do it? Well, which of these factors are fixed? that is dependent upon the system we're going to go into, the speed slash RPM of the machine is fixed at 60 hertz or 50 hertz, depending upon where we're going. So all those things are set, whether by generator design or by the operating parameter, and that leads us to the question of what's variable. The only thing left that we can vary is the magnetic field amps, the strength of the field. So that's the whole job of the AVR and the excitation process, is to produce this variable magnetic field that'll be used to generate the output voltage. Here's a really important thing that I really want to get across. I want everyone, if nothing else, get a couple things out of here, and this is one of them. In a rotating iron, they call it spinning iron, in a rotating iron machine, we produce a voltage. As a generator manufacturer, as a generator supplier, all we can do is produce a voltage. So what, and please speak up here, what the output current and power factor are dependent upon what?
Slip.
I beg your pardon?
Would it be the slip?
No, not quite. Anybody else? Once we generate the voltage, all we do is generate a voltage, but the amount of current that flows, and thus the power factor or power quality of that, are dependent upon, and I've got a new message, by the load. Very good, Cliff. You're right. The load. There we go. The load applied. All we can do is produce a voltage. And this is difficult for some customers to understand when it comes to talking about power quality, which is really going to be a concern for almost all power systems being built today. We're seeing more and more VFDs, more and more LED lighting, both of which have a lot of harmonic content, a lot of dirty, if you will, current consumption on them. And the customer's like, well, my load works just fine on this generator, or works just fine on utility. Why isn't it working on your generator? What's going on here? So you have to explain that all we can do is produce a voltage, and that sine wave is generally pretty pure. There's things that go on, such as winding pitch, that varies the shape of the waveform slightly, but generally it's a solid waveform. The impedance of the generator is different than the impedance of the source of the utility transformer, and so that can lead to differences. But all we can do is produce a voltage, and you have to find a nice way to tell the customer is, your power factor is what you're doing to the voltage we produce. And that can be difficult discussion to have sometimes, especially with the cost to correct some of these power factor, power quality considerations. Next is the air gap. Talk about that for just a second. Again, the lower we make this gap between the rotor and the stator, the more efficient our machine can become. As you know, when you take two magnets, a north and a south, and you're bringing them together, at some point they snap, or they pull each other together. That magnetic field gets stronger with an exponential factor to the distance. So exponentially with the distance. So as you put them together, you get more and more efficiency out of it. And so these pieces come into play here as you get closer and closer to get a much more cleaner and much more efficient machine. And here we are stitching these together again. And these are all tied and stitched to tie these together in order to prevent these forces from ripping them apart. The other one was kind of laced together with almost like a needle and thread kind of combination. This is hand tied. This is this special fiberglass tape, and they're pulled real tight, knotted, twisted, tied, and then glued in place to hold all these windings together, because this is a tremendous amount of force if you have a fault. Okay. So we want to keep the windings from being disturbed, physically pulling themselves apart or breaking a connection, or moving and coming in contact with the rotor because they were moved in the fault. So in this case, when you put the pieces all together here now, So now we're going to take the Y sine wave. Well, we spin this rotor past here, we generate a sine wave. So if you watch this animation at this point, the highest alignment produces the most voltage. As we go out of alignment, the voltage goes to 0, and then it comes the other direction as the other pole alignment comes up. I didn't put north and south on here, but conventionally a north aligning rotor with a south aligning stator produces the peak part of the voltage. If you look at the vectors that are generated, and of course, engineering, we love vectors, don't we? So here's your rotor spinning past. And as your rotor spins past, you can see the different phases come up. Okay. Here's C phase comes up, B is going down, A is coming up. A is peak, C is down, B is coming up. As it spins around and around, these pull together and produce these different voltage vectors. And we draw them as vectors. It's easier to talk about that way. But so as it spins past, it pulls these up. In three-phase generation now, we've got 3 coils spaced 120 degrees apart as they're wound into the stator of the machine. We spin our magnet. In this case, we're spinning it counterclockwise as north-south goes around. So I'd like you to look at this drawing for a second, please, and tell me, where are we at this point in time? So obviously we're aligned with A phase. B phase and C phase are 120 degrees apart. So using conventional current flow, using connections at the other end of the machine, where are we at this point in time? A vertical line on here will tell us. We're aligned with A. We're peaked on A. Are we peaked on the high part of A or the low part of A? Top of A or the bottom of A? Well, if you're using conventional current flows, you're going to have it here, the bottom part of A, not the peak, the valley of the A phase, because here you're lined up with south on the magnet. And it's just the kind of convention we've used in construction. Of course, it doesn't always have to be that way, but the important part is we're producing 3 voltage vectors physically separated by 120 degrees because the windings in the machine are offset by 120 degrees. So what does that mean to us in time? Well, at a 60 cycle system, they're 120 degrees apart. So the peak of A to the peak of B is 120 degrees. The peak of B to the peak of C is 120 degrees. And one phase from 0 to 0 on A phase, for example, is 16 milliseconds. So 1/60th of a second. The 0 crossings from one to the next, or from peak to peak, is 120 degrees. And that happens at 0.005 seconds. Things are happening really fast. Look at the power quality equipment that's actually measuring these 0 crossings, that's measuring these peaks and sags and swells. A lot of processing power to bring those signals in and convert those over to digital and store those and analyze them and everything else. So this is happening very, very fast, right? So the frequency.
Steve.
Yes.
Oh, sorry. Could you please go back to the previous slide?
This one?
So I guess I'm trying to understand this. So for the peak of phase 1 versus the peak of phase 2, so it takes about 16 milliseconds to sort of go from, I guess, a peak of phase A to phase B, and then also you said that for the crossing, for, was it the blue and the red, and then also the black and the blue, it's 0.0055 seconds, but I guess the peak and that 0 crossing also lined up at the same time. So why aren't those time the same? But instead, but the 0 crossing being much shorter.
Okay. The frequency is 60 cycles in this example, and the inverse of 60 is 0.016. So actually that 0.016 is the time from the 0 of the upward 0 crossing of the black until the next upward zero crossing of the black over here.
Oh, it's per
This-
sine wave. Got it.
Yeah. So
It's a per complete cycle.
right,
Got it.
right. But the peak to peak time, they're 120 degrees apart from each other. So
Okay.
this, yeah, I didn't draw it all on here, but the zero crossing of A here to the zero crossing of B here is 120. 120 degrees.
Yeah, sorry, I misunderstood the pictures, but yeah, thanks for the explanation.
Yeah. Sure. Good question. Anybody else? Anything else? Okay. The speed's dependent upon the number of poles through this equation we all have known and seen before. Frequency is the number of poles times the RPM divided by 120. The speed does not affect the amplitude when our voltage regulator is operating properly. I should have prefaced that this drawing is a system with an AVR, because if you didn't have the AVR, the peak values would be coming down as the speed decreased. But in this case, we're maintaining the voltage with our AVR, but really showing that the frequency just quickly is how fast it crosses zero. It's not dependent upon speed. Sometimes people mix, I'm sorry, it is dependent upon speed. It's not dependent upon voltage. Some people confuse frequency and voltage. They're two different things. So if a 4-pole generator spins at 1800 RPM, and this is the formulas, and we just rearrange them different ways than what we're after. If you're looking at frequency, you take the number of poles times RPM divided by 120. If you look at the synchronous speed, you look at 120 times. So just rearranging that equation different ways. But this is the same basic principle as the number of poles, which is a design criteria of the machine, is fixed. And so we end up a frequency at that certain RPM. Yeah. If you're new to this market, and it looks like most of you are not, but if you were new to the market, I'd recommend that you memorize several of these common speeds. If you're dealing with 60 hertz world, you should know 36, 18, 12, 9s. You don't often find machines in our RICE industry, our reciprocating internal combustion engine, typically run 18, typically 4-pole. Some of them are now 3,600. We're seeing the big machines go to 36. Actually, Cat's revving up some of their big engines to 3,600 RPM. And here's 50 and 400 cycle. I don't know. 400 cycles used by some equipment. And I was doing some military work at one time. I was never in the military, but I did work for power systems and radios and communications equipment for the military. And some of them were 400 cycle. So 400 is still there. I don't know if any of you work with 400, but those numbers are out there as well. So, okay, continue putting it together. Conceptually now, tune in. The engine spins the rotor, establishing the frequency. For practical considerations, we're going to say that speed is fixed. We know it's not from the real world, but for right now, we're going to say that speed is fixed. The rotor has a coil that produces a magnetic field that produces 3 phases on the stator because it's displaced by 120 degrees. So now we've got the spinning magnet spinning past copper conductors in the stator, producing the 3-phase sinusoidal waveforms. When we apply an impedance to these loads, we get a current flow. So we produce the voltage, customer applies an impedance, a current flow is a result. Anytime we have a current flow, we get a magnetic field. So now we're talking about the current flow in the stator as a result of the load applied to the stator. So now the magnetic field in the stator is being produced by the current flow in the stator. This load current flow in the stator produces a magnetic field that actually opposes the magnetic field produced in the rotor. And so now we have a strong magnetic field produced by the rotor, producing a voltage in the stator, a current flow in the stator produces a magnetic field that opposes the field produced by the rotor. And so we have to increase the rotor magnetic field to maintain our voltage. And this is what the role of the AVR is. Okay. And this phenomenon is called armature reaction. And this is really something we'll talk more about in the advanced class, but I'll touch on it here because most of you are pretty skilled and experienced and knowledgeable in this already. But you'll notice that the magnetic field of the rotor appears to be much larger than it needs to be to produce the voltage that's needed out of the system, because it's got to overcome this armature reaction. This armature reaction can be as much as 20–30%. So now you got to have that much more field current. So what that boils down to is that you run a low value of field current to produce a voltage, the rated voltage at a low load or zero load. It doesn't take much current to produce full voltage. But as you start to draw, let's say you went from 0 to 100 amps of load current, your field current might go from a few amps to maybe 10 times that much, because it's got to produce enough current to overcome this armature reaction. So it's the number one factor when it comes to the reduction of voltage while generation is taking place. So some more practical considerations, and this is one I think you'll find useful as well when you're doing your power system studies and analysis, is that how much current will flow in this model. So armature reaction was a reduction in current flow. Now we're going to say if we put a short circuit on the output of this generator, how much current will flow? Well, we can calculate it. We have an ideal source with no internal impedance. The source has a resistance because it's copper wires. Every copper wire has a resistance. It might be small, but it's there. We have lots of turns we've laid into the stator to accomplish this voltage we want to generate. There's 277 turns. We need to generate this much voltage. Anytime you have wires turned around steel, you're going to have an inductance. So it's possible to calculate this. It's a rather complex calculation that has to be done, and it also varies different times depending upon how the field collapses and how the regulator kicks in and reacts to it. But it's a long, complicated equation, but we can make it easy. Let's make it easy. Some areas we need to know are basically three values of current. Number one is, what is the peak value? That's the withstand current. And what is the amount of current the circuit breaker has to interrupt? And what's the long-term welding current that might result from a fault so we don't melt our cables? So three primary places we worry about in our power system study is the peak, the withstand value, and that has how, because again, anytime we have a fault, we have these forces that generate, try to pull things apart. And so we want to hold them all together. We brace our switchgear bus, we tie our cables, we put braces between our cables, and we use a certain torque connections and certain number of bolts on a connection. So if there is a fault, they don't rip themselves apart. So that's the withstand, not the KAIC, but the withstand value of current. And to calculate that, any machine machine has to have on the nameplate the X double prime D. And in this example, we get a pretty close, within a few percent of the actual long, complicated, drawn out formula by simply taking the full load current from the nameplate of the unit, 1203, and dividing it by the X double prime D value. So 1203 divided by 0.16 gives us 7518. So you can tell your customer with a high degree of confidence, this is within a few percent of the actual short circuit current. Now, we're not counting the contributions from external sources coming back into the generator from some external load. No, this is the generator's contribution to a fault, peaks out at 7518 peak value of the subtransient reactance. Okay. We'll talk more about this later on, but this is the value. And here's a real world nameplate. Took a picture of a CAT nameplate, and I just pick on CAT because I can get their stuff. They're really good about posting pictures online and data online. So it's common source. But anyway, here's a picture of a nameplate. out there, and I rewrote the values over here. Grab your calculators real quick, and or your phone or whatever, and do this calculation. So the maximum instantaneous short circuit current is the X double prime D, and the circuit breaker interrupt is the KAIC, and that's the transient reactance of the X prime D. So do this calculation real quick for me. Help me out here. You're probably asking yourself, which X double prime D value do I use? They actually use the per unit. So it's 1128 amps we got off the rated current, 1128, divided by the per unit X subtransient reactance. Get you 8917 amps. So little less than 9,000 amps short circuit, peak short circuit value this can contribute. So that's the peak, the top mount value. That's the withstand current for the ATS and for the switchgear. How long does it take, anybody, how long does it take for a circuit breaker typically to detect a fault and open its contacts? Anybody know? Detect a fault, trip the operant linkage, collapse the link, and open the breaker. Anybody know what that time is? You actually buy them this way.
Less than 3 cycles.
Mm-hmm. Very good. Exactly. 3 cycle. You can buy 5 cycle breakers too, but 3 cycles is a typical value. And 3 cycles is the more difficult value to do. So the interrupt current, the KAIC, the interrupting current, is calculated from the 1128 again, divided by the transient reactance per unit. And so that's the amount of current the circuit breaker has to interrupt. Typically, you'll see circuit breakers with a 10,000 amp KAIC. Well, this would be fine in this application, wouldn't it? Right? So a quick way to calculate these values, and if you're into short circuit analysis and study, we'll talk a lot more about that in the future, but this is the peak value of the withstand. So that's the top of the fault, and then as it decays down to the next level. Okay. Another consideration of generators is called winding pitch. And I go exactly how and why this happens in the advanced class, but basically let's say that to make machines smaller, lighter, cheaper, manufacturers started overlapping A and C. Remember how we saw on the vector diagram, as the rotor went past, we saw one phase coming up as one phase was going down, as one phase peaked. So at the peak of A, you've got C going down and B coming up. And so they've laid A and B, and they've laid B and C windings in with the A windings in a ideal pitch, in a one-to-one pitch machine. All the windings under the pole face, the rotor pole face at that time, are all the same phase. Well, they started laying the other phases under the pole face at the same time in order to make the machine smaller. They found they could make the machine smaller, lighter, cheaper. But what happens is they sacrifice a little bit the waveform. So here is, they've overlapped the windings in from B and C onto the A windings. And so as it spins past, we actually have 2 different generators in my drawing here. One generator is a one-to-one pitch machine, and one generator is a 2/3 pitch machine. And anytime we have a difference in voltage, like we have here, there'll be a current flow. This current flow, we see it, we manifest, we see this as a reactive current flow. It's actually a 3rd harmonic current flow. So if you look here, this is the difference between generator 1 and generator 2. Right here has produced this part of the sine wave. Here it's produced this part of the sine wave. Here it's produced this part. And so anytime we have a difference in voltage, we have a current flow. The analogy I use is jumping two car batteries. If one's at 10 volts and one's at 12 volts, you're still both positive voltage, but you're going to pass current from one to the other because of that 2-volt difference. Here we're seeing a generated voltage in the third harmonic, and we see harmonic voltages on our system as VARs. Okay, see it too. We see them as VARs, and we think to ourselves, well, don't we have VAR regulators? Can't we turn the VAR down? Well, we can, but we can't get rid of this. So if you parallel machines with different pitch, you're going to get a harmonic current flow. Now, will this hurt you? I don't know. It depends upon where you're at in your system. But if it's a small amount of current, let's say you're running two machines that are running about 30% or 50% current each, and you add 10% of third harmonic current flow on top of that, it's probably not going to hurt it too much. If you're running 80% current on these machines and your harmonic current flow is now 20% because it's going to go up as your load goes up, your harmonic current flow is now 20%. Now you're going to take a chance of overheating the machine and damaging the end turns. Remember, the windings went down the slots, went across the end turns, and came back the next slot. You'll damage those end turns on the machine. And so you want to eliminate that. So you, generally speaking, and if I can have one takeaway from this slide, that is, don't parallel machines with different pitches, especially if you want to run high on the load curve somewhere. Low on the load curve probably won't be a problem. High on the load curve, it definitely will be a problem. That's winding pitch in a nutshell. Any questions on that concept before we go on? That's a really important concept, I think. Anybody seen machines parallel with different pitches? Okay. Well, think about it when you do. When you go to apply it, and typically you'll see it. Years ago, I would have said if you stick with the same manufacturer, you'll be all right. But CAT, for one, was offering generators built by one manufacturer. They don't make the alternators, obviously. They just buy them, vary them for their gen sets. But they were buying alternators that were 5/6 pitch. And they wrote article after article and technical paper about how great 5/6 pitch is. Then they changed vendors, and the new vendor has a 2/3 pitch. And so now they're writing papers about how great 2/3 pitch is. But you still shouldn't be parallel on 2/3 as 5/6 machines. It's not as big a difference as a 1-to-1 and a 2/3, but still it's something to consider. So there's some good papers on this. If you go to Cummins, has some good white papers, and they have a very good white paper about this winding pitch phenomenon and how you can prevent it. But their number one clause is don't do it. Get a different alternator. There's things you can do. You can put an impedance in the neutral leg to block a filter, essentially to block the third harmonics. Often AHJs won't approve an impedance in the ground because the code says solidly grounded, and they see a reactor in the neutral leg and they freak out. So it doesn't often get passed by AHJs if you do that. You can switch neutrals on and off. I've seen in some cases they'll switch. If they have a very low neutral content, they'll actually have one contactor in the neutral and turn the neutral off, open the neutral to ground link, or open the neutral connection and just simply take the face-to-face connection. So there's things that can be done, but generally don't parallel machines with different pitch. I know I made a big deal out of it because that's a very common mistake that happens. Seeing no questions, I'm going to keep moving on. As you know, so far we've been talking about windings being laid in the slot 120 degrees apart. We're back to our black, red, blue, our three-phase windings here. You can bring them out and connect them in different ways. You can connect them in a Y or delta. It doesn't really matter. The machine doesn't care. It depends what voltage you get out of the unit. So this is a 6-lead machine brought out this way. But if we took these black windings, let's say, and we split it in half and brought it out halfway through, we could end up with a dual winding like this. The same number of turns, It's just the windings are brought out halfway through, so we can have a 12 lead machine now. So you can put them in a series combination parallel type setup to get your dual voltage machines. So you can have your 240, 480, you can have your 208, 120, but you can, by reconnecting these windings together, you can get different voltages out of it. Okay. Just be careful when you do. The polarity is critical, of course. If you connect them together in series, you get the higher voltage. You get just single times the current, but you get the same power out of the unit. Where you parallel connect them, again, same power, voltages, lower current is higher, and you get the same power out of the machine. Obviously, if you connect plus to minus, it's a problem, right? I mean, if you connect, sorry, plus to plus, it's a problem. You want to series them up properly. And there's ways you can tell. We used to have one of the tests we did when we were doing our new winders was actually cut the leads off and say, okay, figure out which winding goes on what machine. And you can do it with a voltmeter and a battery. You can flash a bump them, and you can figure out which winding pairs are there. So it's possible to figure out a machine where all the markings are cut off the end of the wires. You can still, with an ohm meter and a battery, figure out which one goes where. Three-phase winding connections, of course, can be delta or Y. Sometimes we'll see a floating Y, sometimes wild leg delta. These are just different configurations, more in the power system side than the generator side. So we'll kind of let that fly for now. But you get different voltages, and if you look at the alternator data sheet, it'll talk all about that. What are we doing here? Hey, we got to move along. Okay, protecting and testing alternators. Seeing no questions, you can move on. Well, we talked about what can be damaged in the alternator. We saw this picture before, right? We talked about the insulation system and the winding system are the two things we need to worry about. In the insulation system, we have the insulation between phase to phase, phase to ground, and turn to turn insulation. We need to protect all that. The other is the conductor system or the wiring system itself. And normally we have to prevent that against thermal damage from over current over time, or what's called I squared T damage. As you know, thermal heat is generated as I squared times time. So that's the thermal damage of overheating a winding due to excessive current flow through it. And it might not be fundamental. It might be harmonic current flow. It might be some other frequency, but it's still current flow through the wire causes it to overheat. And the other type of damage you have to worry about is mechanical or vibration. We don't talk a lot about that in the class. That's an external thing, vibration control, but it's very important because you want to tie the windings tight and prevent problems from happening. So that's the other type of vibration that should be protected against in a machine. When you go to test a machine, you want to test the insulation, and again, this part of the class is kind of geared towards the hands-on individual that's going to be out testing and installing new machines. A meg ohm meter is basically a multimeter, especially a multimeter, puts out a higher voltage. Low current but a high voltage to stress the insulation. Okay, a standard digital voltmeter will actually measure the same ohmic range, but it's only putting out typically a volt or two. It doesn't really stress the insulation any. So why is a standard digital voltmeter not a valid test of insulation condition? Because it's not stressing the insulation. You want to stress the insulation a little bit and see if it's going to hold up. And so a meg ohm meter allows you to do that. It's a DC voltage anywhere from 500 to 2,500 volts, hand cranked, or perhaps so these guys are battery operated meg ohm meters down here, but they still stress the insulation and read it for you. Okay? Insulation testing, just be careful when you do this. You can damage a machine if you're using too high a voltage, like a 2,500 volts. Megger on a 600 volt machine could possibly cause a damage of the insulation. So be careful. A 12 lead machine, you tie 10 of them together and take the last two, which is one winding, and you meg that to all the rest of them. And you go around and meg each one together. So point to point, be careful of capacitive effect. There'll be a voltage built up and stay on those windings for a little bit. So use a jumper to discharge them. The next is a turn-to-turn or short detection. And so inside a machine, if it is a turn-to-turn short, remember we talked about 1 volt being generated every time it went down through that field. Well, if you miss 1 volt out of 277, it's probably not going to be a big deal, but it could overheat over time. But if you use 3 or 4 or 5 of those windings, now you're talking about, you know, getting into the 3, 4, 5% differential in voltage, and that can cause a problem with your balance and your symmetry of your power system. So we use a ductor to read that. And again, this is really handy up front when you have a new machine. You take these readings and you document them and save them. You can come back then to your machine a year later, take another set of readings and see if you have any turn-to-turn shorts, because this resistance will change. It's a high current resistance measurement, where the megger is a high voltage impedance measurement or resistance measurement. This is a high current, low resistance measurement. So you apply a 10 amps or 100 amps, and you measure the voltage drop across the winding, and you document that. So it's best if you have this as found reading upon initial startup, jot these values down, record them all, and use them in the future. All right. Next is exciter checks. Again, this is critical for every system. You should check every time you do an outage, you should check every diode. We talked about missing a piston on your car and not having the power. Well, you start to lose one exciter diode, you probably still make voltage, but the other diodes are going to get stressed even more, and soon they'll start failing, and they'll start failing, and they'll be stressed. And so you really need to check it every maintenance. A lot of techs don't like doing it because you have to take the end bell off, you have to take some bolts off. It's not an impossible reading. Sometimes the orientation of the machine isn't very conducive to doing this test, but still it should be done every time, and make sure they're all there. Another, it's very handy to have startup values again. So we're looking at, during startup, I run it to full rated kW. I measure the amps, the volts of each phase. I measure the excitation current everywhere I can, the excitation voltage, and make sure it's all there. So I have that information going forward. And brush systems, you check the brush, the wear. This is where you get your fish scale out, get your boss to buy you a fish scale. And you put the paper between the brush and the slip ring, and you put your fish scale on the pigtails and pull slowly until the paper falls out. It tells you how much force the spring is applying to the brush on the slip ring. I don't suppose you have many slip rings out there. If you want to talk more about that, get you a ring. I'll walk you through that process. Frequency effect comes into play. We obviously have respect to those that are dealing with 50 hertz world. I use 60 hertz in my slides just because that's most of where our training takes place, in the 60 hertz world. But the 60 is a fundamental frequency, does the most work for us. The others are all losses, they're all power that are generated harmonics due to disturbances in the system, sometimes in our control, sometimes beyond our control, but still the fundamental frequencies and the harmonic content. This came into play recently for me. The consulting work at an installation had a lot of LED lights and a lot of VFDs. And between the two of them, they were producing so much harmonic current that's actually causing a problem overheating the machine. So we had to put in chokes and filters and things to eliminate some of these high harmonic contents. Graphically, it looks like this. Your fundamental is the black line. The fundamental plus the third is the red line. So what you see is essentially the red line in this case on your scope. The third harmonic is then this small green wave line. So if that's the fundamental with third, the resulting is the red line. See, it's not really a sine wave anymore. Keep that in the back of your head for a second. When you add the fifth harmonic, again, you're going to see the red. The fundamental is the blue. You won't actually see that anymore. And the green is the fifth harmonic. The 11th harmonic, the combined harmonics. Now it doesn't even look like anything, because now the sum of the harmonics is actually this green wave down here. The sum of all the harmonics with the fundamental is the red line up here. So I'm sorry, the red line is what you see on your scope. Really hard to read and see. But let's make this easy again. Just like we made the calculation of short circuit, let's make this easy. Use a power quality meter. Some panel meters have this THD function built into it. Often gets ignored. Or you use a aftermarket power quality meter, flip on CTs and clamp on voltages, and you can actually measure this THD. On the generator data sheet is a THD limit. Typically 6% in that ballpark, 5-6% typically is the THD limit that you want to stay below. And if you start to go above that, then you run into trouble with your exciter, because exciters sometimes look at the zero crossings. Sometimes some of the protective equipment looks at 0-volt crossings of the voltage waveforms, and with waveforms like the one we just saw, you have extra zero crossings, it's going to cause a problem. So THD limit is on there. You talk to your customer and say, like, your load, again, I produce a voltage. It may not be a pure sine wave, but it's pretty close. May have a little distortion because I may be a 5/6 or a 2/3 pitch machine, but my sine waves are pretty close to sinusoidal. And your load you're applying, Mr. Customer, is causing harmonic content to flow. And reacting with your load is causing this heating in your generator. It can damage your generator. So be careful of that. The next is reactive capability curve. We're running shy on time. I'll try to wrap this up on time here. I know you guys got to go. There's the rotor. At the end of the rotor, there's the intern. In the stators, the interns go back and forth. The end of the rotor has a lot of things going on. What happens is the interns can be overheated if you're underexcited due to all the different current flows in that area. So the solder ends up melting, and I've actually seen them where I saw a picture recently on the Facebook Genset Tech page that showed picture of a winding, just one black winding all the way around the intern of the machine. And that was due to overheating of one phase. It could be caused by a load imbalance, but it could also be caused by the underexcitation on that one. So if we draw the line, the reactive capability curve, with the kVAR and kW, and you're familiar with this because this will be your power triangle, will be down here on this part of the curve, right? So we draw on here the stator thermal limit. Any more current than that out of the stator will start to damage the windings of the stator. This is the I²T of the stator. Here's the I²T of the field. Any more current out of the field will damage the field windings. So we don't want to go beyond that. The interns on the top part is interns be overheated and damaged. On the bottom part is slip damage, because if you start to reduce the excitation, you start to break this magnetic bond that is locking the rotor to the stator. And if you break this magnetic bond, you slip. So your rotor will slip past the stator. Well, it was north to south bonded together. The next is north to north, which repulses each other. So once you get the first break on the pole slip, you go to pole slap. And again, we'll talk about that more in the advanced class. But it sounds like a hammering, machine gun kind of sound coming out of your generator. Very bad on machines. They can tear themselves up really quick. So you want to avoid slipping, which is the bottom part of here. So now we've got these three overlaid on the KW kVAR chart, and that becomes the rated operating point. So on the nameplate, your data, your machine, it'll say so many amps at, just put the word at between each one. So many volts at so many amps at such a power factor at such an excitation current at, and that becomes that operating point on your machine. This becomes the operating region where you can safely operate that machine. Manufacturer says you're in here, you're okay. You're outside here, you're in trouble, right? Well, you should protect against from getting outside that operating range. In the US, we typically draw that curve this way. Okay, I say the US because this has been the US standard for a long time. We have kVAR on the vertical axis. On the horizontal axis is kW. So this point is up and to the right on this curve. Our European friends take it and spin that curve the other way to where you now have your power up and down, actual power, kW this way and kVAR on the horizontal axis. They spin it and flip the curve over. So if you're looking at a European manufactured unit, this will be the reactive capability curve. This is a rated operating region for this machine. They just do it different over there. Some quick discussions on temperature. Okay, you need to stay within that curve. And what I didn't show here, I don't know if I can draw it or not, but your power triangle that you know and love, the power triangle, is KW on the horizontal axis, K bar on the vertical axis, and KVA becomes a diagonal. And for some reason I can't draw. Every time I go to annotate on here, I go to the next slide, but there's a triangle that the power triangle becomes in this part of the curve. Let's talk about temperature real quick. We're down to the wire here, but the important part about ambient temperature is the temperature as it enters the generator, not the enclosure. Okay, you can't stand outside. You got to get right at the generator enclosure point, and that's the entry temperature, or the ambient temperature from the generator's eyes. That's the ambient temperature entering. The temperature leaving the generator becomes the ambient plus the rise, or the operating temperature. So the standard ambient, both books have run about 40 degrees C. Obviously, you're going to have higher temperatures here and there, but that's the standard. In some insulation classes, it'd be 40, some it's 80. Again, get it from the generator data sheet. Temperature rise is the outlet temperature minus the ambient temperature. Again, take your thermometer, dry bulb thermometer, measure those. That's the rise. Okay. Again, manufacturer's data sheet will tell you the rise reading of this machine. Often we heard 40 over 40. Now we're hearing 60 over 80 in some cases, but that's the temperature rise. If you start to exceed that temperature, you're going to decrease the life of the machine. Okay. So the ambient temperature compensation, if the outlet temperature starts to exceed the rated value, you should reduce the load on the machine to prevent the outlet temperature getting too high. Or in some cases, you can control the ambient temperature. Maybe you have radiator coolers, maybe you have fans, blowers, I don't know, whatever you might have to cool the inlet air. But at any point, you want to maintain that outlet air to not exceed the outlet temperature. If you do, you run into problems with temperature ratings and decreasing the life of the machine. The rule of 10 states that the operating temperature of the insulation system will be reduced by 10, the life expectancy is doubled. So if you increase it by 10 degrees C, for each hour it operates 10 to C overrated, you're taking 2 hours off the life of the machine. Okay? We have a rated expectancy of 25,000 hours, but still, if we do too much, we're going to reduce it by overtemp. And that makes sense. Overtemp, reduce life. Humidity is less and less of a factor today than it was in the past. Today's insulation systems are less dependent upon organic compounds like paper and more dependent upon plastics to be the insulation material. So it's not as much of a problem, but still you should have strip heaters in condensing atmospheres in cold climates, just to keep the temperature of the generator a few degrees above ambient. Turn it off when it runs. Fungus and salt, again, less of a problem now, but the older materials would actually be a food for fungus, and so it would grow. New insulation materials don't support fungus growth, and so it's not a much problem anymore. But if you're dealing with old machines, you might, if you want to replace an old machine, it's got some unusual ratings, you may want to look and make sure that your new machines in the high humidity environments work well with that type of environment. The next is dust and sand. Obviously, you suck in dust, it acts like a sandblast and rips the insulation apart. I know I got kind of quick here at the end, and at the first, we think we made it up. Just a quick review, we talked about the different types of power generation, some fundamentals of where it comes from, the construction, how they're made, and how these systems work in a generator. I hope this was a good introduction for you. If you have any questions, I welcome your at any time. There's my email address and my phone number. Give me a call. I'd love to talk to people. I often get, I don't say frequently, but maybe once or twice a month from old students that call me with questions. I welcome them. And in a humble show of respect, anybody recognize that motor from anywhere? That was the elevator motor out of the World Trade Center. That's in the World Trade Center Museum. And that's a synchronous machine that ran the elevators. You see how it blew apart when it oversped at the end. So we covered a lot of ground. Any questions, anybody?